Hello. We're very briefly going to talk about an additional method for analyzing two-dimensional steady problems. So we've already talked about 1D steady and transient problems with no dimension and transient problems with one dimension. So now we're going to talk about steady problems that are dependent on two dimensions. And this is going to be a very simple analysis using what we call the conduction shape factors. It turns out that analytical solutions aren't very practical for many two-dimensional problems. Typically, we have to use some formula such as separation of variables to solve these 2D problems. And that makes the mathematics complex, and the solution is usually in the form of some kind of infinite series. So we take advantage of numerical solutions or simple analytical solutions to define what we call the shape factor, or S. The shape factor basically takes the place of the thermal resistance, and it's determined by comparison with experiments or numerical calculations. So for comparison, we can actually look at the plane wall and show that the shape factor is just surface area over length, or wall area over length. So for that 1D problem, we have that 1D shape factor. For a cylinder, we can look at this definition and see that the shape factor is here, this 2 pi over the natural log term. And so on. We can do this for spheres and so on. Now, shape factors have been tabulated for many types of problems. You can look in Table 2.3 in the textbook for the course by Krieth. And then once you know the shape factor, you can add it to your thermal resistance problem. And then you can approximate various systems using those tabulated shape factors to get a reasonable estimate for the total heat transfer or the temperature difference. So it's not an exact scientific solution, but it is a good engineering approximation that allows us to come up with an answer that we can use to make a decision on our design process.